pressure management. So looking at the 4-arrow diagram, which you've seen a few times today, we tend to put pressure management up at the top, and we tend to show it with an arrow both upwards and downwards, because obviously you can increase pressures and decrease pressures. But you want to try and, in this case, to reduce leakage, to reduce that box, you want to bring pressures down. And it's not by accident that it's put at the top of the box, because the big advantage, which I'll come to later on, is when you do pressure management, you're likely to reduce the number of leaks that break out, which actually means that you don't have as much work to do on repair or detection. So I'll cover the principles of pressure management. Now, the point is, this is a little quote. It's been ascertained that the waste from defective pipes and fittings is much greater during the night than during the day on account of increased pressure. To reduce this and thereby relieve the fittings, various forms of pressure reducing valves have been applied. Now, you might think that was a quote from IWA Waterloss Conference 2008-9 in Cape Town, but no, that was in the prevention of waste and water. A student of the Institution of Civil Engineers, a student member, in his paper to the Institution of Civil Engineers on the 8th of April 1881. So we're not talking about something new. And here again, among methods of reducing waste otherwise than by limiting the hours of supply, which the previous guy called the evil of intermittent supply, that of regulating valves in each district by means of reducing pressure has been noted. Principles of Waterworks Engineering, 1897. So there's lots of experience out there. We've been doing it for a long time, so it's nothing new. The big advantage, if we look at the sort of things that Ken has talked about, awareness, location, and repair, and other things about what determines how much leakage, what volume we lose, then if we take those sorts of things here and we look at our actions that we can do, then pressure reduction can actually tick 3 boxes. It will reduce burst frequency, it will reduce the flow rate at which any leaks are leaking at, and it will reduce this thing called background leakage. We haven't really used the term very much. The concept of background leakage is that the fact there are sort of very, very minor leaks out there below the level of detection. By definition, therefore, you can't find them, you can't repair them, you're not going to reduce the leakage. The only way of reducing them is by pressure reduction. I know this guy's ticked another box here, selective mains replacement. I personally doubt that. From my own experience, when you do mains refurbishment, you probably their garden, they might actually get fed up with standing there if it's only breaking out, and therefore your repair costs, and it will reduce your economic frequency of active leakage control. So for the same level of leakage, you can actually go and do active leakage control less frequently. And if to try and explain that, we have this concept of background leakage. Like I say, we can't change that. On top of background leakage, we have the idea of unreported leakage, which will gradually accumulate on the system if you don't go out and do any detection work. When you do detection work, you find those leaks, the unreported leaks, and you reduce the leakage level, and then, lo and behold, unreported leaks break out again. On top of that are reported leaks breaking out every now and again. You find them quickly, repair them quickly, so the actual volume lost is relatively small. So that's the sort of general pattern of leakage going on your network. When you do pressure reduction, then you've reduced the level of background leakage. The rate at which new unreported leaks are breaking out has reduced, so this triangle looks smaller, and then the frequency of which reported leaks are breaking out has increased, so the gaps between these have increased. So you've reduced all three types of leakage. Slight downside, you reduce pressure, which may make leaks more difficult to detect, particularly on plastic systems. Customers may notice reduced pressure, and you may have an increase in customer complaints, but you should train your guys well to manage that. Quite often, people have experienced high pressure in the past and may have actually screwed their stopcock down. When you then do pressure reduction, they get quite poor service. You guys should go out and have a look and check that their stopcocks are open. Some of your reservoirs may not fill at night, but generally speaking, part of your design will be to make sure you'll get water up to the top end of your highest reservoir. Fire flows may be affected, so you may have difficult discussions with your fire services, fire authorities. I had very many difficult discussions with my fire authorities, such to the extent that at one stage we were up to then referring them to being pressure reduction schemes and pressure reducing valves. I came back from a meeting and my managing director said, I'm having terrible problems. It's been hauled onto the television with the fire services, and we were risking lives and all sorts of things. So he says, what we're going to do about it? So I said, well, we'll rename them, not pressure reduction schemes and pressure reducing valves, but pressure management schemes and pressure management valves. So from then on, we have pressure management valves, not pressure reducing valves. Valves and zone boundaries have to be monitored and maintained. If you have a pressure managed area, controlled with shut valves, if those are opened, then all sorts of things happen. I can quote you examples where some leakage inspector opened some valves one night, suddenly high pressure is introduced into the adjacent area, and we have like 10, 15 bursts in that night. So you have to be very careful, particularly with boundaries. You might have a slight loss of revenue, particularly if the person who's guarding the water is on a meter, but okay. I think you get far more benefit of leakage savings than a little bit of loss of income. So, although in some respects you might say, and a lot of people talk about, well, just renew all your pipes, you'll solve your problem. Yeah, but the cost is absolutely phenomenal. Pressure management, pound for pound, is by far the most economic way of managing leakage. I'll go through some of the mechanics. This is a very simple formula for the loss of water through an orifice, a fixed orifice, so that shows that the volume lost is proportional to the pressure, to the square root of the pressure. But in practice, we find that not all leaks behave like that. And what we found is that there are some fixed area leaks which do vary to the 0.5, the fixed orifice in a metallic pipe, but there are other leaks which vary to a higher ratio than this 0.5, and we find values easily 1.5, and in this case we believe that the size of the hole, the size of the orifice, is actually increasing with pressure. So not only does the flow through the hole increases, but the size of the hole increases. And that particularly happens in plastic pipes. So we've got this concept of two fixed area leakage and variable area leakage. And there's a terminology called FAVAD, with fixed area and variable area discharges, to cover that. So when looking at this in the past, we've tended to have the concept that perhaps leakage varies to some power of the pressure. And so we invented this number. This is, when I say we, this is the IWA Water Loss Task Force, invented this concept of N1, it's called, such that leakage is some factor times pressure to the N1. And we believe that N1 was constant to thereabout. Small changes of pressure, N1 is almost constant. And we set about trying to find those values. And generally speaking, we found that the values will vary between about 0.5 and 1.5. If it was a fully metallic system, then the number looks more like the 0.5, which is this curve here. If the system is primarily pressure, then we're getting numbers much higher than 0.5 and perhaps towards the 1.5, or even numbers like 2.5, and you get things like this. And so, generally speaking, you find that most practitioners since 1994 have used the N1 power law that I've just talked about, and they've used it as a fixed value, and they you can do what's called an N1 test on your network to actually assess give you an estimate of N1, and that basically involves just measuring the flows in the middle of the night, looking for when the flows have stabilized, then you drop the pressure by X meters, see how much the leakage has dropped, and therefore you can just quickly work out what N1 is. So in order to do that, we would recommend that you must use what's called the average pressure point on the DMA. In other words, you look at all the properties in your DMA, preferably all connected to GIS, and therefore you can work out where the average property height is, and then you look for a hydrant close to where that average property height is, approximately halfway across the supply of your zone, of your DMA. As I say, wait until the middle of the night when flows have stabilized, and then work it out. Recent developments have shown that, in fact, N1 isn't constant because of that two-part formula of some of your pipes will be metallic, some of your pipes will be plastic, and because they have two non-linear relationships, then in fact the combined effect of that is that N1 isn't precisely constant. And so the recent work is showing that N1 is a function of pressure, and there are ways of estimating it. And this is a graph which shows that. So whereas if reasonably high pressures in a network, then you might do your N1 test, and provided you're doing your own. How am I doing for time? All right. Oh, I can't speak for another 4 minutes. Except to say, can I just? I just thought I'd take this advantage here. We did have a question and answer session at the end of the Water Loss conference. I think it was in Manila, and I really wanted to try and make this point, but I didn't manage to get Tim in time. He disappeared off to the loo or something, so I didn't get this point in. So I thought I'll have a go this time, and that is, my view is, do not use pressure management to cover up leaks or use it as an excuse for not doing proactive leakage management. Yeah? I believe there's a lot of people in the world think, I'll just stick a pressure management valve in and that'll reduce my leakage. If you've got leaks out there running on the network, the best thing you can do is go out there and find them and repair them, because they do not go away. there is no such thing as a self-healing leak. So, what I would recommend you do is you set up your pressure management area, so you get your technicians, get the drawings out and think, right, this is a sensible way to control the pressure. You tend to have to, it's almost like the DMA design things. Quite often you combine both the pressure management areas and DMAs, but now we're looking to go sub-DMA, so now we have DMAs which might have 2 or 3 or 4 pressure managed areas within a DMA, and you tend to be looking now to go along hydraulic contours, if you like, to manage pressure more accurately. And I must admit, this is when hydraulic modelling does come in and help you quite a lot. So you'll do your design of your pressure management area, valve it off. You then do let it run for about a week or so and do what we say, make sure it stands up, which seems a bit of a peculiar phrase, but we do tend to say that, don't we? In other words, I've now valved this off, same process as for the DMS. You valve it off. Before you put your DMA meter in and put your PRV in, don't commit yourself to that expenditure. Make sure that that DMA will maintain supplies during your peak demand periods. If you haven't, you've got to redesign it a little bit. Perhaps reduce the size of the area or what have you, change the valving. So make sure the area stands up, then install the pressure control valve, but do not commission it, yeah? Okay, but you've got it all in, you've done all your hard work, you've got the valves in, all the bypasses, don't commission it. You're still running the network on that pressure. Now do your proactive leakage detection while your pressures are still high. Ken would love it, you see, gets a bit no noise coming through your leaks. Locate the leaks, mark them up, but do not repair them. Yeah, get that blue paint out, spray it all up, graffiti all over the roads, mark them up. Now you commission your valve, then you repair the leaks. So you've got the pressure down, now you can repair the leaks so they won't break out again when they're now at the lower pressure. Thank you.
Time control.